All right, what we're looking at here is it goes back to our vectors where we add vectors. And the example I'm going to give you, there's a couple of different examples you can use. There's the example where we use a plane and it's flying along and it's got a crosswind. That's a nice one. But this is the one where you've got a river. It doesn't have to be a river, it could just be a tidal track. This could be Takabuna, Taka, this is Rangitoto. And you're planning to swim across, as people do sometimes. And maybe this is where the lighthouse is, and you're going to swim from here. But tide's coming in, so we've actually got a, I don't know, let's make that 0.8 meters per second tidal flow. And you can swim at 1 meter per second. All right. So the question you ask, that would be 3,600 meters in an hour. Not a bad swimming, right? 3.6 k's is not too bad in 1 hour. But anyway, you can add these velocities. So yeah, you can swim relative to the water 1 meters per second, but the water is moving relative to the ground, 0.8 meters a second. So your velocity relative to the ground will be these two vectors added, a 1 and a 0.8. So your actual velocity is this red one. So you have to go off from this angle, and you knew that. So your actual velocity at the end of the day is relative to the ground. You can use Pythagoras. So it's going to be 0.8 squared plus 1 squared, and that's 0.64, 1.64, and we take the square root. All right, this calculating to do 1.64 equals 1.28, so we'll make that 1.3 meters per second. So you go a lot faster than you can actually swim. All right. Now we can also work out the angle. If it's the angle to the bank, right? So the angle to the bank, angle to the vertical, they have to tell you what. So theta, we can use Pythagoras, right? And for these little guys, I've already worked out the 1.3, so I could work it that way. I often like to use inverse tan, which is opposite divided by adjacent. So inverse tan is going to be inverse tan, shift tan, and I've got to do my little division, so I will put it in little brackets. All right, if I use the calculator, don't know if you can see that, so I'll do it again. So I go inverse tan, where's tan? Open the brackets, and I go opposite 0.8 divided by 1, close the brackets, equals 38.6 degrees. So now I've got the angle, but be very careful and read your question, ask which angle were they talking about. Now what we can ask here is, and a very common question, is how long will it take to get to the other side? And you could go, okay, now I'm going at 1.3 meters a second, and I'd have to work out what the distance is. Now, basically, if we come back to this one, sorry, then you're heading off at this angle, right, that we just calculated. So you have to work out the distance to get to the other side. And that's the tedious way of doing this. Because yes, that speed, 1.3 meters per second in that direction, if you work out this distance, you can do it. So it might only be 3 k's or 3,000 meters like that, but on the angle, it's going to be a lot more. So you could work out the distance, and we could then do our calculation, remembering that velocity equals distance divided by time, so time equals distance divided by velocity, right? So the time to get across would be that. No problem. But there's a nice way of doing this, which is this. You know you've got to get 3,000 meters across there. You know you're going off at that direction at 1.3 meters a second. And you know eventually you'll get to the other side. But your velocity is composed of two things, two velocities perpendicular to each other, don't interfere with each other, they don't subtract from each other, so you're always going to have your 1 meter a second that way and your 0.8 that way. So to cover this vertical distance, or this distance this way, the only part of your velocity that does that is this. Alright? And we're saying you're going at 1 meter per second. So it will take 3,000 seconds to cover the vertical distance So that's the time, 3,000 seconds. If you'd worked out this distance and divided that distance by your velocity, you'd have got the same thing, 3,000 seconds. If I want to know how far I end up down away from the lighthouse, if that was the lighthouse, then it's just 3,000 second time 0.8. Right? Velocity times time. So what we've done here, though, is a very important principle for projectiles, which we're going to get to. And that's that when you've got a velocity, you can break that velocity down into two components, a horizontal and a vertical. All right? And this is really important. All right.